share screen. Let's see. Can you see the slides?
Yes.
Okay, perfect. So today's topic is really fun. It's recommender systems. What we're going to do, I mean, there's tons of work and approaches for recommender systems. So I'll show you one of the most popular ones. And the important thing is that you get the setting and, you know, the understanding of the problem rather than, you know, a particular approach. Okay, so this is the outline. So the idea of recommender system is the following, right? You have a system that predicts the rating a user would give to an item. The idea is I want to recommend items to users, whether it's you know, in a shopping website or, you know, other types of recommender systems like, you know, movies platform or music platform or something like this. I want to say to the user, these are the things that we would imagine that you would like. And in order to do this, I need to predict, or I cast the problem into predicting what is the rating of a user for a particular item. Yeah, and if the rating is high enough, so let's say 5 or 4, then I recommend that item. So typical scenarios is, you know, one very popular example is Netflix. So Netflix recommends, you know, shows based on what you've watched before, and they kind of predict the rating that you would have on things that you haven't seen. So shows that you haven't seen, they would predict, okay, what is going to be your rating? If you have watched it, how you would have rated it based on ratings you gave for other shows. Another example or scenario is, you know, online shopping, when they recommend, you know, these are the things we recommend that you buy based on your previous shopping or ratings that you provided on previous items. So the problem formulation is as follows. So you're given M items and U users. So you have a big system or a platform which has, you know, multiple users and multiple items. And you want to predict the rating of a user U, a particular user, for an item M. The ratings are typically from 0 to 5, but of course can be anything. But in this lecture, we assume the ratings are from 0 to 5. Here's an example of, you know, how your data set is going to look like. So you have a set of items, let's say movies. So you have 5 movies. You have, you know, a number of users, not 5 movies, right? Like a large number of movies, of course, a large number of users, and you have the rating of a user for an item. So user 1 rated item M1 or movie M1 with 5 stars. He rated movie 2 with 5 stars. He didn't rate movie 3 because he hasn't watched it. So question mark means there is a missing rating. M4, he did not like it at all, so he gave it a rating of 0, and M5 a rating of 0. Similarly, user 2, he gave a rating of 5 to M1, did not watch M2, gave a rating of 4 to M3, 0 and 0 for M4 and M5, and so on. Now our job is to do what? What is the machine learning problem that we're trying to solve? Is to predict these question marks. What are the ratings of these users on items that they haven't viewed yet? Based on what? Based on the ratings they provided to items that they have rated. Yeah, so this is the game we're playing. Okay, good. So just the terminology that we're going to use in the lecture. We have M is the number of items, U is the number of users. RMU is a function which is equal to 1 if user U has rated item M, and 0 if he hasn't. So basically here RM3 and U1, or RU1 and M3 is equal to 0. RU1 and M1 is equal to 1 because, you know, user 1 rated M1. Okay. YMU is the rating given by user U to item M. And of course, this is defined only if R of M and U is equal to 1. So here you have Y of M1 and U1 is equal to 5, Y of M2 and U1 is equal to 5, and so on. Okay? There are 2 types of you know, recommender systems out there. One is called content-based recommender system, and the other is called collaborative filtering recommender system. Let's start with content-based. So items are typically associated with a set of features, X1, X2 until XD. So these are explicit features that are, I know about the items, whether it's a shopping website or, movie rating website, it doesn't matter, right? These are just some features of the items. And each item, M, has a vector of feature values. So basically, for X1, item, let's say M1 has this particular value, for X2 it's particular value, and so on. And for each user, you want to learn a vector of weights, WU. Yeah, so every user has its own vector of weights, corresponding to what? Corresponding to these features. So what is the most important features that determine the rating for the user? Yeah, so the hypothesis is given a movie M with its feature values, X1 till XD, and a particular user, use the weight of the user, the weight vector of the user, you do, a linear combination of the weight and the features. Typically similar to any, supervised machine learning problem we've looked at. You have a set of features, you associate a weight with every feature that determines the importance of the feature, and use this as the final score. Let's see an example, a concrete example. So let's say I have, again, in the movie rating website, I have these users, these movies. Now the features could be what? Any thoughts? It could be
genre.
Genre, exactly.
Actors.
What is that? Actors, exactly. So actors could be also, the duration,
length,
the duration, type of the show, whether it's a series or a movie, language, all of these, properties of the movies. And every movie would have its own, values. So I can turn these, even if they're categorical, I can turn them into numeric values. Yeah. By normalization and whatsoever. Yeah. So now I have, a feature vector for every item, for every movie. Okay. So now I'll associate a weight for every user. He has their own weight vector, and the rating should be predicted as a weighted sum of the weights times the feature value. Yeah, so that should give me the rating. Yeah, what does this user care about more? Is it the genre, or is it the type of the movie or the show, or is it the director, or the actor? And that has different importance for every user, different from each other. Okay, so our goal is to learn these WU vectors for every user in the system. Based on what? Based on the ratings that I already have. Okay, so learning these ways. Let's see how do we do that. So again, right, as we said, our MU is 1 if the user has rated the item M, and YMU is the rating given by the user. So I'm going to minimize the mean squared error, similar to any supervised machine learning problem, and it's a regression problem because I want to predict a value between 0 and 5. Sorry for this green thing. I think I did annotation. So I want to say, okay, given that I set these weights to these particular values, how well do I predict the ratings that I already have? Is it close or not? Okay. So basically, this is how I formalize it. Yeah, it's summation for every user. There is an error, and the mean squared error per user U. It's summation over all the available ratings that user U has given to any item M. What I would predict the rating to be, so WU transpose XM minus the actual rating the user gave. And I do squaring of this to do, mean squared error. So I want to see, okay, according to my weights, if I set them to a particular values, okay, am I getting the rating of user 1 on movie M1 to be close to 5, yes or no? And the further it is away from 5, the bigger the error is. Yeah, so ideally I want to get them to be, to predict these ratings as accurately as possible, these weights. Okay, so that's over one user. What about this term? So I added this term as well. So lambda,
normalization, regularization.
Exactly, regularization. I make sure that I don't do overfit. Yeah. And lambda is the regularization parameter. Excellent. Now I can do this over all the users. So I have this error per particular user. I can sum over all the users. So from user 1 to capital U, this error per user. Yeah, that gives me the error over all the whole data set that I have. Yeah, and I want to minimize this overall error. Yeah, and what is the parameters that I need to learn is this WU, weight vector per user. Yeah, where the dimension of this vector is equal to the number of features that I have. Okay. Questions? Good. Okay, how do I minimize the squared error, guys? What do I do?
Derive.
I
Derive.
differentiate and equate to 0. Perfect. So I differentiate with respect to what? With respect to WU and equate to 0. So I'm going to do exactly this. Okay. So I'll use a gradient descent because this is not, and if I differentiate and equate to 0, I'm not going to get a closed form. So I'm going to use a gradient descent, similar to neural network. Yeah, because the objective function is not, it would not lead to a closed form solution. Okay, so what is gradient descent? Remember the gradient descent, you initialize the weights at random, and then you update the weight based on, the gradient. So, particularly do the learning rate times the gradient, and you subtract this from the current weight. Okay, so I'm going to do this. So the gradient means what? Means the derivative of the error function with respect to WU. Okay, so let's do that. Okay, I have here, this is the easy part. So I have 2, it will become 2 lambda WU, okay? And I have originally WU here, so WU minus eta times 2 lambda WU, that becomes 1 minus 2 eta lambda W, okay? So that's the first part. Minus 2, because I have 2 here, so I get minus 2 eta, because I'm multiplying by eta, and then the gradient of this function, of this whole thing, component with respect to WU. Now, this summation would go away because I'm summing over, I'm differentiating with respect to WU, one particular user. So all the other values, all the other WUs will go away, and I remain with my particular W that I'm differentiating with respect to, or updating the weights of, yeah? So basically I get WU, of course summation here, this stays, and then I have XM, so WU transpose XM minus Y MU, right? Because I'm driving this with respect to W, right? It's the, whatever is inside the square, and then I have times the derivative of this with respect to WU, which is XM. Okay, so this is really what I get of the gradient descent. So now if you look at this formula, I have everything is known. Yeah, I have WU is the old weight, W is the old weight, XM is the feature vector. So for every movie that I have, I multiply the current weights by the feature values, minus, and then subtract the rating that I have for this particular movie, XM. I'm summing over all the movies, yeah, that I've rated. And then multiply again by the feature values. That gives me some values, some vector. You subtract this from this vector, and you get, right, the new vector W, or the new weights. Okay? Any questions about this? You're gonna implement this in the next assignment. So ask questions. We're gonna give you a starter code because this is a little bit too involved. So we don't have libraries that kind of do this in a straightforward way. So we're gonna give you, starter code that you can build on. Okay, good. So collaborative filtering recommender system. That's really the content-based recommender system in a nutshell, nothing else. Now, what is the problem? There is a problem that we have, or an assumption that we made that's kind of unrealistic, yeah? Which is?
That we have the data of the user.
That we have the what?
What the user likes and his ratings.
This is a good point, right? So what happens if I have a user that doesn't have any ratings? How can I predict, ratings for them? We'll address this, but the more, crucial problem is the following, that I'm assuming that these features are available. So every item I have exactly all the features for it, yeah? In principle, I don't know what is the feature. So it could be that, you know, yes, genre matters and director matters, but it could be that the user is looking at combinations of these. So it's not that he, you know, genre is independent from director, from actor in general, or in a lot of cases, right? So let's say if you're not talking about movies, if you're talking about shopping, that you don't have these features. You don't know exactly what these features are, or you don't have them. Yeah. So that's what collaborative filtering is. Yeah. So the idea is that you assume there are a set of features x1 till xd, but you don't know them. You don't have them explicitly. Yeah. And you try to learn them as you learn the weights as well. So you do what is known as, you know, dual learning. You're learning the feature values and you're learning the weights. Okay, so what does this mean? For each item M, we learn a feature vector xm, and for each user U, we learn a vector of weights W. So the only assumption you make is that there are D features, yeah, but you don't know exactly what these features are. Again, what is the final prediction that I'm going to make is going to be a weighted sum of the weights times the features, yeah? So this is how it looks like. You have these items as before, you have the users, you have some ratings for some items, and then you have these D features, but you don't know them. You don't have any values for them. And you still want to learn, you know, this weight vector for every user. Yeah, so let's see how to do this. You understand the difference? Okay. So let's say I want to, so this is done in a iterative manner. So you're learning the weight and the feature vectors together. So assume that you're given the x1, x2 until xm, okay? You want to learn the weights w1, w2 until w, I guess wm as w, 1 second. So yeah, I think here you just x1, x2 until xd, and you learn the weights w1, w2 until wd. There is some typo, yeah? Okay. So what do we do? Again, I minimize the error over all the weights, or over all the, you know, the users that I have and all the items. Again, the mean squared error. So we're just assuming that I have these features, right? And then we'll see how do I set them in the beginning and how do I update them. So I need to learn these two things, the feature values and the weights. Okay, so the same thing, I have the mean squared error function, and I have the weights, and I want to learn the features. So I guess, yeah, here I understand this W1, W2 until WU is the weight vector. So it's not a type, it's just the weight vectors of every user, right? So each one of them is a vector, and X1, X2 until XM is the, you know, the feature vector of every movie, yeah? So this is what I wanna, the values of every, of the features for every movie. Okay, so what do I do? Assume that I have the features, I learn the weights, and then assume that I have the weights, I can now learn the features. So I need to, you know, differentiate this or do the gradient of this with respect to, you know, WU to get the weights, and then I need to do the, you know, derivative of this with respect to XM to get the features. The iterative approach works as follows. Let's initialize first X1, X2 till XM as random values. Yeah, so I just say, okay, I don't know anything about these features, I'm gonna set them as random. Now I have them, I assume that I have them, and I do exactly as I did with the content-based, you know, recommendation or filtering, yeah? So I basically do learn the W1, W2 until WU by minimizing the mean squared error. So I do gradient, and then I do gradient descent. So I get some weights, okay, based on random features. Now, what do I do next? I learn X1, X2 until XM. Now plug in the weights that I have, fix them, you know, and I'll apply gradient descent, assuming that the unknown is XM rather than WU. And that gives me new feature values. I then repeat this again. We use these new feature values to update the weights. And now once you have new weights, use them to, you know, learn new features, and so on until you get convergence. What does this mean? It means that the X's and the W's do not change much. Understand the intuition? Questions? Okay.
So I don't get how this works.
Okay.
It's like
Hmm.
the values are random. We
Start
start
with
and
random.
then like we train the W's based on random values.
Yeah. So based on random values, you get not very good values. But as it goes on and on and on, it converges, right? It basically tries to learn that the properties, the values of the movies based on not a particular user. It's looking at all the users. Yeah, that's why it's called collaborative filtering. It's looking at similar users to you. So users have rated the same items with similar ratings. Yeah, you learn from them. So you want to minimize the overall error, and that learns from similar users. So you end up with features, right, that based on ratings of other people that are similar to you. So this is how the intuition behind how it works. Is it clear now?
Okay. Yeah. Thank you.
You're welcome.
I have a question, sir.
Yeah.
So what we're trying to do here is to learn the features, right?
Learn the features and learn the weights.
Okay. Also the weights. So your assumption is you have the data, but you don't have the features
Yes.
that corresponds for this data, right?
Yes, exactly.
So what kind of data is this? I mean, the features are the columns, right? The columns head.
So you have
Headers.
this. You have the ratings only.
I don't understand how can you have the data without having the columns, the features.
You have only the ratings. You have that I rated movie 1 as 5.
You don't have. Okay.
Only the rating,
Okay,
right?
okay.
You don't have anything else about the items like actor, director, etc. Or you don't know what are the
Okay.
features that matter. Okay?
So we assume some features and then we learn upon them.
Yeah. Basically, these are implicit features, right? That we wanna.
We don't know what are the features exactly, so we just randomize them.
Exactly. We randomize them and then we update them until they converge.
Using the error function.
Yes, exactly.
Thank you so much.
Well. Okay. So let's see this simultaneous optimization. So how do I minimize E? Let's say I have set XM at a certain iteration. So I have some values for XM. How do I get WU? What do I do? Gradient descent, right? So I initialize X1 and these X's. So the initial step is to initialize both the X's and the W's to small random values, and then minimize E using gradient descent. So I minimize it, right? So I get XM. This is if I'm doing, differentiation with respect to XM, I get exactly this formula, right? To XM. Here I don't forget that I added something. I had a regularization parameter for XM as well because I'm learning that, yeah. And I again don't want to overfit to the training set. So I added an additional. Yes.
When do we stop? What do you mean by converging?
It means that the values do not change anymore. So basically, this W's and the XM don't change anymore. You go in another iteration, they stay the same or within a small threshold.
Sir,
Yes.
the regularization parameter are the same for both.
No, you can
for
do
WS.
different regularization parameters. Yeah.
Okay.
Okay. Other questions? Okay. So basically, right, I initialize the X's, I initialize the W's, and then I do update the XM based on gradient descent. So if I differentiate this with respect to XM, I get 2 lambda XM, so 1 minus 2 eta lambda XM, because I have, right, 2 lambda XM, and I have, right, the XM minus eta times the gradient. So I get 1 minus 2 eta lambda XM minus 2 eta, and then this summation, right? So I do this, the differentiation of this with respect to XM. I get WU transpose XM minus YMU, right, times WU, because I'm differentiating with XM. Okay. And then I do the same thing. So I differentiate with respect to WU. We've already done this in the content-based filtering, right? So basically I get, this is the way to update the WU, okay? And now I update XM based on the current WU values, update WU based on the current XM values, and then, you know, continue until they don't change anymore, and then predict the rating finally as WU transpose times XM. Any questions about this? Because this is what you're gonna do in the assignment. Okay. So what happens? So somebody brought this up. What happens when you have users with no ratings? What will be able to do? So let's see what happens. Yeah. So this is the mean squared error with respect to a particular user. And let's assume this user have no ratings at all. So a new user like you, right? You just joined Netflix. How do I recommend something for you? Typically what you do is you minimize the EU, right? Now I don't have any items that the user has rated, so this summation goes away, and I end up with just lambda WU all squared. What is the values of WU that minimizes this error function? Lambda WU squared.
0.
0, exactly. So WU would be 0, would minimizes the error of this user. Okay. So basically the prediction would be 0 for any item M. Since I'm gonna use this way to predict the rating of the user for an unknown item, all of the items in that case, then I'll get 0 for every item in the database. So basically I wouldn't be able to recommend anything for this user. Okay. So what do you do? What would you do if you have, you know, a new user coming in? How would you recommend the items to them? Any thoughts?
I recommend the most commonly used items by other users.
Exactly. This is exactly what we do. So we use mean normalization. This is the technique that does exactly as you said. So sometimes you give a list from the beginning to choose from. So if they do that, right, then they're trying to avoid this issue. Yeah. So this is a good point. So for instance, in Movie Length, this is a website for movie recommendation. They ask you to rate at least 20 items once you join the new show. I think in Netflix they do the same thing. They ask you, rate some movie. Yeah. But if a system doesn't do that, what would be the best second option is to kind of say, okay, I'm gonna recommend to you what is the average, user likes, or what is the most liked movies overall users. Yeah. So this is done. We can do this in the platform or in this framework by doing some mean normalization. What do I mean by this? I mean, I compute the mean average rating for every item M that I have in the system. So what is this? It's basically the average of all the ratings and that the users have given. So it's 1 over the number of the users for that item that rated that item, and then summation over these ratings. Yeah, that gives me the average rating per the item, for every item. And then,
sorry,
yes.
Is that an issue?
What is that?
This? You said قبل شوية إنه it's an issue to do this. They were trying to do what Hadi said for them to be avoiding this issue.
Yeah, so why is it an issue? Because sometimes people don't like to go and join a platform and provide ratings. So these ratings typically are taken explicitly, are measured explicitly. So most of the people, I don't rate any show on Netflix. Do you? Do you guys rate movies on Netflix or shows that you watch?
No.
No, you don't. You just watch them, and they assume that you like it because you continued the whole series. Exactly.
So these are most likely implicit ratings that are learned based on your behavior or your interaction with the items. So then if I haven't watched anything, I'm a new user, there is no way I will have to. I'll provide any implicit ratings. Yeah. So to overcome this issue, this is what you do. You typically do this mean normalization thing and recommend to the new users the items that are or you assume the average rating per item for these new users. You got it? Okay. What does the denominator mean? It means the following. It means basically how many users rated this item M. So count the number of users that have rated the item M. So I do the mean for every movie M that I have, or every item M that I have. I count how many users have rated this movie. So that's what it means, the denominator. And then sum the ratings of these guys and divide by this number. That gives you an average rating per item. Yeah. So let's say I have 5 users, all of them has rated it 5, then the average would be also 5. Okay, good. Now, what do I do so I can use the exact same framework without changing anything for these users? I do the following, right? I subtract the mean from every rating that I have. Yeah, and I will see how this helps. Again, after I do that, I learn the weights W1, W2 until W capital U, and X1, X2 until XM, the features, using this, simultaneous optimization technique that we've discussed. And then finally predict the rating of a user using WU transpose XM. Okay, plus the mean rating. So for those new users that have not rated any item, their W's is going to be 0, but then you're providing the predicted rating for them would be the average rating for all users that have rated the movie. Yeah, so basically, let's say I am joining Netflix new. What is going to be my rating for, I don't know, Ozark or whatever? Then it's going to be the average rating of all users that have watched Ozark. Okay? And so on. Questions? So let's see an example. So I have the following. I have this, matrix of ratings. These are the user. Question marks means the users have not watched these movies, and hence we don't have any ratings for them. Again, these ratings could be implicit, yeah, based on, the longer you've watched the show, or if you finished it, then you have a 5. If you stop midway, then you have a 3. If you watched only 10 minutes, then it's 0, and so on. Yeah, so you don't have to be explicit. Now, the mean of the ratings for the 5 movies that I have are 2.5, 2.5, 2, 2.5, and 1.25. Let's see why. So 5, 0, 0, so it's 10 over 4. I'm counting only over the people that have watched the movie. So I have 10 over 4, that's 2.5. I have here 5 and 0 over 2, that's 2.5. I have 4 and 0 over 2, that's 2, and so on. So I get these averages per movie. Yeah, so I have a vector of averages per movie. Okay, now what do I do next? I subtract from the ratings the average ratings. So 2.5, 2.5, because it's 5, 5. 0 becomes minus 2.5, and 0 becomes minus 2.5. Okay, second one is 2.5 minus 2.5 because it was 0 minus 2.5, and so on. Now I have this matrix. This is the matrix that I'm going to use to learn W's and to learn the features. Once I have them, I add, I always, when I'm predicting, I multiply the weights times the feature values and add the average rating to compensate for the subtraction that I did when I was learning. Okay? Questions? And that will overcome the issue of,
I have a question.
Yes, go ahead.
How many features would you initialize? It depends on your data. The question is number of data you have, maybe divided by 10 or 20, maybe, I don't know.
Yeah, it's a hyperparameter, right? So you can start with 10, you can try 20. It's a good question, right? So 100, you can try a few different values and see which one.
You tune it.
Yeah, you tune.
Okay.
Yeah.
So
Yeah. All right. Okay, so it seems we're gonna finish before we need to go in another session. Yes, so this is the last slide I have on this topic. Okay, finding related items, and that's what I'm gonna ask you to do in the assignment as well. So let's say now I've learned the weight for every user based on this technique. Now, how do I find related items? So in this recommender system, they give you, here is the movies or the items that I expect that you would like, and I can do this by thresholding. I say, okay, this item for user 2, let's say I predicted that this rating, the question mark here, is for M2 basically is, let's say, 4. And my threshold is if it's above 3, I recommend it to the user. So that's how they would recommend the items. I would say, okay, if it's above, the rating is above 3, predicted rating is above 3, then recommend the item. So I would recommend this one. Let's say this was 2, then I wouldn't recommend it, and so on. Yeah, so this is how I recommend the items. Now, in these recommender systems, you also provide related items. So if you remember the Amazon example, it typically shows you, people who purchase this item also purchase these items. That's kind of explicit, but they also recommend, you would like these other items because they are similar. Yeah, they have the same features as this other item. So in other words, how do I find, related items? I can use the feature vector. So given an item M, I can compute the distance between M and every item M dash based on the feature vector that I've learned, XM, as just the norm. Yeah, so basically Euclidean distance or Manhattan distance between the feature vector of M and M dash. Yeah, so let's say M is 0.9, 0.8, 0.7, and so on. And this is 0.9, 0.7, 0.2. I do just subtraction, point-wise. That gives me the distance. And now to receive the top K most similar items to M, rank them based on, this distance. That gives me the closest one to item M. Okay, that's pretty much it. We have less than a minute. Let me know if you need me to start the meeting again, if you have questions or anything.
Yeah, I have a question, like a small question.
Sure.
So will neural networks work, or because it's linear, it wouldn't? It would be better to use a linear
any
model.
model can work. Yeah, so any model can work.
But didn't you say neural networks need non-linear functions?
Where is
Activation functions?
Yeah, true. So when basically you don't have a model. So let me rephrase what I'm saying, right? Because as I said, there are multiple approaches for recommender systems. In this approach that we've discussed, we're using gradient descent. We're building a model on our own. Yeah, so there is no you're not using linear regression or support vector machines. We're using a model from scratch. This is the model, right? Just using
okay.
Yeah, but there are other techniques where you could use neural network recommender system, other approaches that you could do this. Yeah, but it's, the setting is the same. You want to predict the unknown ratings for a given set of items. You could also use matrix factorization for this. Yeah, but this is something that is a little bit advanced.
Okay, thank you.
Other questions? Okay, I'll ask Sherry to again do a lab session for you for the next assignment, and it should be straightforward. So you'll have this and the ensemble learning, a question on ensemble learning as well.